Welcome to the Physics Tips for Cambridge Students YouTube channel, and today we are going to be looking at uniform circular motion. Now in this particular video, we are going to be focusing on the radian and expressing angular displacement in radians. We are also going to be looking at the concept of angular speed as well as the concept of linear speed. Without much further ado, let's get started. Now, when an object is undergoing circular motion, the speed is constant, right? The angle is continuously changing. Okay, the speed is constant, but the angle is continuously changing. I think I've got something to show here. All right. So as you can see, the speed is constant, but at a tangent to the circle, but then the direction is constantly changing as well. So there is a velocity. Now, you have been taught in lower forms that the acceleration is always directed towards the center of the circle, as well as the force, the resultant force, which is the centripetal force. So we are going to be looking at that in the next video. Now, as I said, the speed is constant, but then the direction is constantly changing. So there is a velocity as well as an acceleration. Examples of circular motion include a stone being whirled round on a string, a CD on a record, or a record spinning on its turntable, and satellites moving in orbits around the Earth. Now, let's start by looking at the conversion between the degrees and the radians. Now, the radian is the SI unit of angle. The radian is the angle subtended at the center of a circle by an arc length S equal to the radius R. So looking at this diagram, the arc length that is swept in this from this position to that position is S. Now the radius of the circle described there will be R. To get the arc length is going to be S is equal to R theta. Okay, R theta. So now to get the angle, you then make theta the subject, which is arc length over the radius, which is equal to S over R. S over R. Now for a full circle, that is when the object is gone through 360 degrees, you have 2 pi radians. But how do you get these 2 pi radians? From the formula, we're saying that S is equal to R theta. So the radius is R, the theta that has been swept is 2 pi. So which means the circumference is 2 pi R. Now to get the that is theta will be equal to 2 pi R over R, which is going to be 2 pi radians. Okay, so we have gone through a complete circle. That is S will be equal to circumference, which is equal to 2 pi R. Okay. So 2 pi R over R from this formula would give you 2 pi radians. Okay. Now, the formula that, the definition that you need to remember is this one, which of the radian, saying the angle subtended at the center of a circle by an arc whose length is equal to the radius. Now, 1 radian is equal to 360 degrees over 2 pi, which gives you 57.3 degrees. Now, we can also use the formula but using pi radians, because 2 pi is 360, so pi will be 180 degrees. So suppose you want to convert theta degrees to radians. So it's going to be, since 180 is pi, what will be theta degrees? So theta degrees will be theta over 180 times pi, which is going to be simple proportion there. So you have a choice either to use 2 pi radians, but remember to use 360 on there, or to use pi and 180. Now, when changing degrees, radians to degrees, you say theta in degrees is equal to S in radians divided by 2 pi times 360. Or you can say S in radians divided by pi times 180. I hope you remember that. Now, next we are going to look at linear and angular velocity. The linear velocity v is the velocity of the object. Is the velocity the object would move off at along a tangent to the circle if there was no centripetal force. Okay, so the centripetal force is there to keep this object in a circular motion. So if there is no circular motion, centripetal force, then the object would move off at that tangential velocity that we have seen in the early video. Right, angular velocity omega, or we can call it angular frequency as well. This is the rate of change of angular displacement, just as much as linear velocity is the rate of change of linear displacement. So the angular displacement is theta, so we can say omega is equal to theta over t. Now we know that when we have swept a complete angle of 2 pi radians, the time taken there will be a period t. So which means that omega can also be expressed as 2 pi over the period t. Okay, 2 pi over t is the period. Okay, so theta over t right there. Now, angular speed is the angle in radians swept out by the radius per second. Okay, angle in radians swept out by the radius per second. The unit of angular speed is radians per second. Radians per second. Now, we look at the concept of period frequency, linear and angular velocity. The period, or the time period, is the time taken to complete one revolution. That is to turn through 2 pi radians. So the time for one revolution is t, big T, which is equal to angle turned 2 pi over the angular velocity omega. So this must be always remembered. T is equal to 2 pi over omega. We had found that there again t is equal to 2 pi over omega from this one. Then frequency is the number of revolutions per second. So we can say F is equal to 1 over t. Hence, omega is equal to 2 pi over t, which is equal to 2 pi f. For one revolution, the speed v is equal to the distance moved over the total time taken. Distance moved will be a complete circumference, which is 2 pi r, and the time taken will be big T, which is the period. Now, if you say 2 pi over t, that is omega, times r, that gives you omega r. So speed is equal to omega r. The linear speed v increases with the radius of the circle, but the angular velocity is constant. So the angular velocity is kept constant, and v is proportional to r. In one of my videos, the third video, I'm going to be doing it, like to showcase an experiment. Remember, you are going to do in the paper 5 how like the design. So in this, the purpose of this design is to see the relationship between v and r for an object undergoing circular motion. Right, so please don't forget to subscribe to the YouTube channel, as well as pushing the notification bell, as well as liking and sharing this video to as many students as you can. This is the end of the part 1 video. Part 2 video will focus on centripetal force and acceleration. Signing out.